vector basics. So the first time, let's look at some notation. So this is point A right here. And you know it's a coordinate point rather than a vector because of the parentheses. So this is point A, and it's located in three-dimensional space at 5, 3, -4. And this is point B, also, given parentheses. And then we could find the vector AB. Remember, a vector is going to be signified by an arrow starting at A and going to B. And it's very easy. It's very similar to like a slope idea, in that if I'm at 5 and I go to 10, I went over 5. If I'm at 3 and I went all the way to -2, I went down 5. And if I'm at -4 and I went all the way to 6 in the z direction, right, the depth, the dimension, then I went that way 10. So the vector AB, denoted by the arrows, is in three-dimensional space 5, -5, 10. And that would be the vector AB, which would be different than the vector BA. They would point in opposite directions. However, they would be the same size. All right, scalar multiplication. So take this vector A, and then if you look at what 4A is, well, 4 is just a scalar, meaning it's just a number. And if we're taking 4A, we're just looking at the exact same direction. However, it's just 4 times longer. 4A also should just be A plus A plus A plus A plus A. And if graphically you can think of adding these arrows, you're adding them tip to tail. So it would just be boom, 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 boom. And you just have 4 of the exact same vectors. Well, it's in the same direction, and it's just 4 times longer, which means each piece of the vector is 4 times longer. So to take 4A, you can just multiply each piece by 4. To add vectors, so now this is vector A. Now up here, this was point A and point B and vector AB. Okay, now normally we just say vector A. So this vector A is already a vector, and we're going to do A plus B. And you think about, well, all you're really doing is adding each part. If you look down here, this is like a vector A plus some vector B in picture form, and you got an arrow plus an arrow, and the resultant is the addition of the things, meaning the combination of the two. You add them tip to tail. So if you just took this vector and went this way, or rump, and then went that way, or rump, well, the resultant is the idea of doing both of those things. So if you look at vector A is saying go 3 to the right, 4 up, and 12 depth. Vector B is saying, well, this is 7 to the right, 5 up, and 3 depth. Well, if adding them together, you did the combination of those things, you'd end up going 10 to the right, 9 up, and 15 in the depth. So really just adding each part. Just as a reminder, vectors could be forces, velocities, accelerations, torques, momentums. There's all sorts of things in the physical world that are vectors. So if you think of these as velocities, this could be the plane's velocity, and this could be the wind. And what you're saying is that you're moving 3 meters per second to the right, but then the wind is 7 meters per second to the right. So then what is your combination of those things? What's the resultant of the plane in still air plus the wind? Well, you're going 10 meters per second to the right. And then that'd be true for each piece. Right, the magnitude. So when you see this, you probably think absolute value, which is unfortunate, but your previous teachers should have talked about the idea of the absolute value of a vector really is the magnitude of the vector. And that's really what the absolute value sign does anyways, even in math. When we take the absolute value of a complex number, we're looking at the length of the vector, of the real part and the imaginary part. Really, the absolute value of -5 being 5, it's talking about the length of the vector, -5, and it's pointing 5 units to the left, which would have an absolute value or length of 5. So if you think about what this is saying, it's really just the 3D Pythagorean theorem if you want to find the length or the magnitude of vector A being 3, 4, 12. Okay, so think about this picture. If you have something that's a 3 by 4 by 12, that means you go 3 over, 4 up, and 12 depth. Well, think about the bottom of this box. If you went 3 over and 4 up, then L would be 5. It'd be a 3, 4, 5 triangle, right? L would be a squared plus b squared equals L squared. But then if you look at this diagonal, let's get rid of those. If you look at going across the bottom and then straight up and then that diagonal, that triangle is also a right triangle. And so you end up with this idea of a three-dimensional Pythagorean theorem. L squared clearly is a squared plus b squared, but then if you think about that, L squared plus h squared equals d squared, and d is the actual length of the vector. D is that diagonal from the bottom left corner to the back top right corner. And so the 3D Pythagorean theorem is true. So anytime you want to find the length of the vector, you can just square each of the three dimensions and then take the square root. So the length of the vector 3, 4, 12 is actually just 13. Okay. All right, the unit vectors. So we have x hat, y hat, and z hat, which is also the same thing as the notation I hat, j hat, k hat. And again, we literally say x hat. Okay, that's x hat. It is the unit vector, meaning it's the vector with a unit length 1, and it's pointed straight right. So that is x hat, 1, 0, 0. It's really just a direction, because if you take anything x hat, you're not actually changing the size. You're just pointing it in the x direction. So anytime you see those, you're really just talking about unit vectors pointing in the direction that they want to point in. All right, now let's say we wanted a unit vector in the direction of vector A. Well, if you think about vector A is that 3, 4, 12 ratio. So we can't screw up the ratio of those dimensions. Otherwise, we change the direction. But we want it to be a unit 1. So think about it. This really should make sense. I'm going to find the length of A, which is 13. And then I'm going to take each component and divide that component by 13. And then this vector is the unit vector that points in the same direction as the original vector A, because the ratio of the pieces, the x hat, the y hat, and the z hat, are the same, except they're all 1/13 of what they were. But if they're all 1/13 of what they were, then the original vector is 1/13 of what it was. But the original vector used to be a length of 13, so now it's a length of 1. So this, taking a vector and dividing by the magnitude, scales down the vector into what they call a unit vector in the direction of that. All right, notation. So this is like the vector notation, and this would be more like a polynomial definition. Vector A is 3i hat plus 4j hat plus 12k hat. In this case, the 3, the 4, and the 12 are really scalars. But if you take 3i hat, you get this. Well, I hat is 1, 0, 0. So then 3 I hats is 3, 0, 0. But if you add this vector and this vector and this vector, we know how to add vectors. We just add pieces and pieces. So if you add those 3 vectors, you really just get back this, which is the same thing as the original. So sometimes we look more like a polynomial definition of this, or we just use the vector stuff. So this is just notation. All right, now there's 2 ways to multiply vectors together, right? We already showed adding, and subtracting is obviously very easy with scalars and such, but there are 2 ways to multiply vectors. And there's not normal multiplication. There's the dot product, and there's the cross product. Let's look at the dot product first. So we want to take the dot product between 2 vectors. Anytime you think of dot product, you want to think parallel pieces, and eventually you're going to think cosine. Dot product, parallel, cosine. The only part that counts is the parallel pieces. And from an application point of view, it's like the work done by a force. The only part of the force that does any work is the force in the same direction of the displacement. So if you're like pulling a box across the ground, the only part of the force that's doing any work is the horizontal part. The vertical force does nothing. Well, it does nothing to do work. I mean, it reduces the normal force and does other things, but it doesn't actually do any work. Okay, so dot product, parallel, cosine, and that's really what a cosine would do when you think about it. So this is how you take the dot product. So if you take the vector A and dot product with vector B, you are going to multiply each piece. So think of this as forces and displacement. It's that force and that displacement to do that amount of work. That vertical force and that vertical distance did that amount of vertical work. And again, work is a scalar. And then the third dimension is the same thing. So take each piece multiplied by its other piece, and then you add them together. And remember, the result of the dot product between 2 vectors is a scalar, not a vector. Again, the dot product of 2 vectors is a scalar. It's just a number. In a physics sense, the dot product between force and displacement is work, and work is a scalar. It'd be 77 joules of work done. It'd be the total amount of work. The other way we can define a dot product is the dot product is also algebraically equal to this quantity. Okay? So really what we have here is two different ways, or two different things the dot product is equal to. The dot product, how we calculate it, it's equal to this, but the dot product is also equal to this. So the dot product between two vectors is equal to the magnitude of A, the magnitude of B, times cosine of the angle between them. And really what you think about here is that you're only multiplying the parallel pieces together. Okay, so if you think about a situation like this, if I have a force at this angle, not all of it is doing work, only the parallel piece. So if you take A cosine theta, you're taking the horizontal component of A and then multiplying by B, and that would give you the work done on that box. Okay, so the dot product has lots of uses, but probably the biggest one is that it allows us to find the angle between vectors. And again, I skipped a couple steps here, but look up here. The dot product is equal to this. This is how you calculate it, but then it's also equivalent to this, which means these two guys right here, this and this, right? These guys, that and this, are equal. So if you can set them equal to each other and then solve for the angle, you can say that if you take the dot product and divide by the magnitude of AB and then take inverse cosine, you actually get this relationship. Think that through. That's just me setting those two quantities equal to each other. And it's very easy to find the dot product. We have to divide by the magnitude of A and B, which is define the length of A and B, and then take inverse cosine. So if I had these two vectors, A and B, they're in three-dimensional space, they're pointing on crazy angles. However, they do form a plane. And I want you to think about that. Go back to your geometry. 3 points determine a plane in space. Well, vector A and vector B both start at the origin and then go out in space. And so then they actually form a plane, AB. And so there is then an angle between vector A and vector B. And if I want to find that angle, it's actually very easy with the dot product. Right? The angle is just inverse cosine of the dot product, which I can find, and then divide by the length of A and B. And so this is what I would do if I actually wanted to find the angle between A and B. I would get 49.4 degrees. Okay? One of the main uses of a dot product is if you actually wanted to show something was two vectors were perpendicular, you would just show that the dot product is equal to 0. Think about that again. The only way that the dot product is 0 is if the angle is 90 degrees. Again, look here. If this guy is equal to this guy, certainly the magnitude of A and the magnitude of B aren't 0. So if the dot product is 0, that must mean that the cosine is 0. Well, cosine of 90 is 0. So if you want to show that the angle is 90 and you want to show two vectors are perpendicular, just show me that the dot product is equal to 0, right? So the dot product being 0 if and only if the angle between the two vectors is 90 degrees. If it's 90, the dot product will be 0. If you can show me the dot product is 0, the angle must be 90. Again, these are non-zero vectors, so the only way it's 0 is if the cosine is 0 and cosine of 90. Okay? There are certainly applications when you get to double block physics and you do you can do magnetic flux, you can do, in this case, electric flux, you can look at the work done by something. It all requires the dot product. So there are all sorts of applications of dot products. But in the calculus sense, probably finding the angle and then showing something's perpendicular is probably the easiest parts. All right, now this is the other way to look at multiplying vectors, and some vectors are the cross product. Cross product, perpendicular, sine theta. Again, dot product, parallel, cosine. Cross product, perpendicular, sine. And in a physics example, those are probably the three most popular ones, right? This is looking at the torque caused by a force. Forces with lever arms cause things to experience a torque, and torques make things spin. So if you're thinking about, like, here's a disc, and then I'm going to take this force and I'm going to apply a force on the edge, and I'm going to make that thing spin. Well, that's going to be a torque. And how we want those things oriented? Well, we want those things oriented perpendicular. Okay, so I'm going to show you how to take the cross product between two vectors. So this is a little like determinants of a 2x2. You can kind of see this really quick, and eventually you probably use your calculator to do this. But so if I have A cross B, I'm going to take the cross product. So what you're going to do is write ijk, and then write out vector A and vector B below, and then you're going to take the determinant. So the cool thing of a cross product, the cross product between two vectors is actually another vector. And again, that's really important. So look at I, and then when you're looking at I, you take that box, and then you do the determinant of that box, which is 4 times 3 minus 12 times 5, and I get negative 48. Okay? Then you cover up J, and you box this, 4 and 3 with 12 and 7. Okay? And based on the orientation of the vectors, you always have to throw in a negative sign there. So then you do 3 times 3 minus 12 times 7, which is negative 75, and then take opposite of that, and so I get 75. So then 75 in the J direction. Then you cover up the K, looking at the K part, and then you do the box there. 3 times 5 minus 4 times 7, and you get negative 13. Okay, so then you have each one of these pieces. So that is then negative 48, positive 75, and negative 13. That is the result. That is the cross product of A cross B. And remember, the result is a vector. Okay, and I want you to think about this. They'll reference the right-hand rule and other things. And again, a lot of people do have physics already when they're looking at this. So when I look at these things about torque and angular momentum and the magnetic force is Q, V, cross B, they have a better understanding of why the cross product is important and why the cross product is the perpendicular piece. But if you're just basically in calculus, you're a little bit behind when I say things like the right-hand rule. This is like a picture version. So if you take A cross B, the cross product C is going to be perpendicular. The cross product is perpendicular to both A and B, always. Okay, so if you take A cross B, well, A and B form a plane, and the cross product is the vector that is normal to the plane, always. Okay, so vector C will always be perpendicular to the plane formed by A and B. A and B will always form a plane because 3 points determine a plane. Okay, so this is how you find the cross product, but the cross product is also equal to this. Okay, the magnitude of A times the magnitude of B times sine of the angle between them. It's basically the size of the force, the size of the lever arm, and the angle between them. Okay, you also want to think about, this is like old school geometry. Think about, let's lay vector A flat, and then vector B goes off in space and they form some angle. Well, think about, we know that all triangles or all parallelograms are just base times height. The base here is the length of vector A. The height of it, well, think old school geometry. The height of this parallelogram, that guy right there, is just B sine theta. Again, that's basic trig. Look at a triangle. If this is B and this is H, and that's the angle, then sine of theta is H over B, which really means H is equal to B sine theta. The vertical component is just the hypotenuse times sine of theta. Sine times the hypotenuse will always give you back that vertical piece. So then the magnitude of A times the magnitude of B times sine theta, well, B sine theta gives you the height. That's then the area of the parallelogram. So, this is a new thing you now know, the magnitude of the cross product actually equals the area of a parallelogram. Okay? And if you want the area of the triangle formed by two vectors, well, then you just take half of it. All right, so think about what you've all done so far. You now know how to take the cross product between two vectors. You know the cross product is perpendicular to the plane formed by A and B. You know that the magnitude of the cross product is equal to the area of the parallelogram formed by two vectors. The triangle is half of that. The dot product allows us to find the angle between two vectors. All very important moving forward, okay? And then the last kind of piece, well, no, there's actually two more pieces. Let's think about three vectors. So now we have vector A, B, and C, and I want to find the volume of the parallel pipehead. And this is the thing I've tried to draw in here. Again, it's not a rectangular prism because none of these angles have to be right angles. This is just a vector and another vector, and they form a three-dimensional shape that we call a parallel pipehead. But think about how easy this is. It's actually just A dot product with B cross C. Because the B cross C gives you the area of the parallelogram, and the area of the parallelogram and the dot product between A gives you basically the area times the height. And again, it's the dot product because it's only the height in the direction of the normal vector, meaning the height needs to be only the piece that goes straight up from your base. And again, this is also symmetrical. A dot B cross C would be the same thing as B dot A cross C or C dot A cross B. It wouldn't matter because we can find the area of any of these parallelograms and then multiply by the corresponding height. Okay, so what you can do is you can just look at B cross C, find the cross product, which is a vector, and then you can take the dot product of that vector with A to find the volume of this 3D shape. Again, very, very important. Another really cool thing is that you can find the equation of the plane given 3 points. And I kind of show this. So give me these 3 points in space, M, N, and P. And what I can do is I can find the vector Mn, so that vector, and I can find the vector MP. Well, those two vectors, I can take the cross product. If I take the cross product between Mn and Np, I will get a new vector, and that vector will be perpendicular to the plane formed by M, N, and P. And it turns out that the cross product is, the cross product I do right here, this is me taking the cross product of the vectors Mn and Mp, and I get this. And it turns out that we know that vector is perpendicular to the plane, but it turns out that vector, we can use those coefficients as the coefficients of a plane. Remember, the equation of a plane is like ax plus by plus cz equals some distance d. Okay, so then I know 1, 13, and 8. 1, 13, and 8 are the coefficients here. Now I don't know d, but I know these 3 points all lie on the plane. So I can use any of those points I want to plug in to actually find what d is. So I used n. So I plugged in 0 for x, 5 for y, 1 for z, and set it equal to d, and I figured out that d must be 73. Thus, up here, that's the equation of the plane. It's got coefficients equal to the cross product, and then I particularly found what this number needed to be to make n on the plane. And again, you could have used m and p. M and p both work in this equation, right? All 3 of these points are on this plane. You could have done either one. All right, and then the last one is looking at, I think this is the last one, yeah, projections. And so we are going to looking at the projection of B onto A. It's looking at what piece of B lies in the same direction as A. So we're making a vector that only have parts of B that are in the exact same direction of A. And so what we want to do here, this is the component of B on A. So this is B dot unit vector. I want you to think that through again. The dot product between 2 vectors makes it so only the parallel pieces work. So if I just did B dot A, that would be multiplying them together. So if I'm doing this, this is me finding the unit vector A, and if I take that and I dot product with B, I'm taking B and multiplying and forcing only the parts of B that are in the direction of A, and I get that back. Again, this is the unit vector A, dot product with B, projects B onto A. And then if you think about this is another way to do it. It's just a just different version. So b dot a all over a squared times that. Again, that's an a, that's an a, that's an a. It's just a different version of this same thing. Okay, and then this is actually me doing it. Okay, cool with this? Again, think about this. This is the dot product dividing by the magnitude. So I just take the dot product quick and I divide by the magnitude, and then I'm finding it, the component of b that's on to a. All right. Okay. These are just some of the formulas. So parallelogram area is just kind of showing how that works. This is just an example. Triangle area is just half. The parallel pipette is just taking a dot b cross c, or any of those versions. Remember, all of those versions are going to be the exact same thing. And this is a proof. You can look at the proof of those things if you want. But hopefully this at least gets you started. I know there's a lot here, but we're going to have to walk through it more. But the idea of all of these things will be at the very beginning of Calc 3, and so they are at the end of most college Calc 2 courses.